given that it's Easter this weekend and that we're in quantum class, I figured we should look at this probably a little sacrilegious about Saint Schrodinger. As long as the tomb is closed, Jesus is both alive and dead. Now, we've gone through this a lot. What idea is this portraying?
It's the same concept as Schrodinger's cat, isn't it?
Yes, hence the Saint Schrodinger.
Yeah, the idea that it's a probability that it could be both.
Okay.
I forget the meaning behind it.
Okay, so the term that it's referring to is superposition states.
And the idea that it's in both.
Yes, the idea that your state, in this case, it's only two possible states, so it'd be C1, well, let's say C0 of state 0, or times state 0 plus C1 times state 1. And you're in a superposition. If you were to make a measurement of the state, you would have C0 mod squared is equal to the probability of state 0 being measured, and C1 mod squared is the probability of state 1. So that's what it's indicating, that you might have a time variation in these constants. I call it a constant here. Now I say you might have a time variation in it. As an example, when you have a radioactive decay, you have a time variation that it's e to the minus lambda t. So as time gets longer, it's a smaller value. Actually, C mod squared, I guess, is equal to that. And C1 would be 1 minus that. So that you have the total probability at any time is 1, but it starts out being most probable in state 0 and ends up being most probable in state 1. But it's always, neither of those are 0, so it's in a superposition of the two. Now, of course, in this case, the reason I said it's, maybe a little questionable is because it's very important to me that we acknowledge that Jesus did die and did return to life, without which we would have no hope of salvation. So I have to get that in there and not leave it on a potentially, he's a heretic. Right. Okay, going back to the spherical harmonics, the topic of Wednesday. We had this equation, this really ratty equation for the spherical harmonics, where recall for me, if you can, what are the M and L?
The values
or not the values, but what they mean, what they tell us.
So we have M and L are two quantum numbers, and I want to say M was magnetic. No.
It does stand for magnetic, but I did not use that at all in my lecture.
Oh, never mind. I got that from the book.
The reason I didn't talk about it is because we haven't talked about how you measure. To match the azimuthal function's periodic boundary conditions, we had to have this m that was an integer. So that's where it came from. Now, what you said is correct. So I will talk about that right now. The m has no physical manifestation until you put your particle in a magnetic field. Hence, the magnetic. The m tells us about the orientation of its angular momentum. The L was the combo of altitude and azimuth solution, right? With the whole Rodriguez formula. So that's where they came from, which is the question I meant to ask, what they're coming from. But what they tell us in an atom is L gives us the angular momentum. And we have not seen this at all, but it turns out that the angular momentum is equal to h bar square root of L times L plus 1. So it tells us the total angular momentum. And m, often called m sub L, is the magnetic quantum number because it tells us the orientation of the angular momentum. Specifically, L in the z direction is equal to h bar m sub L. Now, you look at that and you say, where does magnetic come into that? Right, angular momentum is not the same as magnetism. Have you taken electromagnetic theory? I'm guessing the answer is no. Okay, just wanted to check on that. Well, you probably still have some background knowledge, like what makes the Earth's magnetic field?
Polar. Actually, I want to say what?
Okay, I was going to say I didn't make out what you heard what you said, but then I realized you were saying I'd say. Go ahead.
It's been a while, so I don't quite remember, but I want to say it's the attraction between the sun and the Earth, but I can't remember exactly why.
Okay. It's not, so it's good that I asked you this question rather than assuming you knew. So
At one point I did know.
the Earth's magnetic field, we believe, is created by a geodynamo.
Okay.
What that means is that you have charged particles. In this case, it's going to be iron ions that are going around in a circle. And in general physics, you did cover this. You have that if you have a current, it creates a magnetic field. And so, for instance, you can use, the Biot-Savart law or Ampere's law to calculate the magnetic field created by a current. This is all discovered by Ørsted, accidentally. He was doing a presentation. He had a compass set up. He turned the power on to something else, and the compass deviated. And of course, he's a physicist, so he plays with things. And he determined that it was the power cable that was close to the compass that was causing the deviation when he turned on the power. And from that, he deduced that the electric current created the magnetic field. So we believe in the Earth we have this material going around a circle. Now, it's a little more complicated than that. You need to also have convection to have the geodynamo effect work right. But in essence, If I have charged particles and they're spinning around in a circle, that's going to make a magnetic field. And in fact, you know that electrons behave as little bar magnets. Did you know that? Yes. Electrons behave as little bar magnets. And how do they know that? Because they put them in magnetic fields and they saw them interact with the magnetic field. And in a way that a magnet would, not just the way the charged particle moving in the field would. And so with the electrons, they said, well, it's behaving as a magnet. It must be because the electrons are spinning. And so if you have charge spinning, it creates a dynamo and creates a magnetic field. And so they called the term for the magnetic direction of the electron its spin, because using the right-hand rule, if I had a positive charge and it's going that way, the spin is that way, or the magnetic field is that way. So they call it the spin. Well, we now know that's incorrect. The electrons, we don't know if the electron actually has a physical size or if it has no physical size. But we can calculate it's smaller than yay amount. And it would have to be moving so that the exterior was going faster than the speed of light to be spinning and create its magnetic moment. Not possible. So our conclusion is that the term spin is wrong. Electrons aren't spinning to create a magnetic moment. They just have a magnetic field. So when we talk about the spin, its quantum number is going to be m sub s, the magnetic moment for the spin, even though they're not spinning. Now back to this. We have electrons orbiting the nucleus. We do not know what their path is, but we can calculate the angular momentum because of our quantum number L that says that you have a certain angular momentum of it going around. So, you know, if it's out farther, it's going to have to go slower for that angular momentum. If it's in closer, it's going to have to go faster. But, you know, it's doing whatever to make that angular momentum. And then this M sub L says, if I put it in a magnetic field, how much of the angular momentum is going to be parallel to that magnetic field? And so the M sub L is just telling you about the orientation with respect to an external magnetic field. If you don't have an external magnetic field, you don't see an effect to a first order. I'm not sure if we're going to get a perturbation theory or not, but when you talk about the hydrogen atom, initially we're going to say the only potential energy is the electrostatic potential energy. That's part of the lecture that I might jump to here. But then we're going to say, well, we forgot a lot of things because we have the nucleus, which is a proton. Proton has also a magnetic moment, it has a spin. The electron has a spin. So even if your electron is in a state of L equals 0, L equals 0 is not possible. No, it is. That's right. So even if it's in the state of L equals 0 with 0 angular momentum, you still have this particle has a magnetic moment, this has a magnetic moment, and if they're aligned or anti-aligned, that's a different energy state. So you have different energy based on if they're aligned or anti-aligned. So you have the spin-spin coupling is another energy term. And then if it's in a state where it has angular momentum, well, then you're going to have the angular momentum of orbit coupled with the angular momentum of the spin. And so you have spin-orbit coupling. And so we're going to have to take into account these different other sources of energy that are not just this one potential energy function. There is a third correction that we'll be making, and that is for relativity. I guess there's a fourth correction as well. The fourth correction is we start out by treating the nucleus as stationary. Well, the nucleus is, I forget what the fraction is, but something like 800 times, 1,800 times more massive than the electron. So it's really approximately true that the nucleus is stationary, but it's not technically true. And it makes a small difference in the energy as well. So we're going to make those corrections later on. I don't know why I got into that. All of this to talk about those quantum numbers L and M, so that these spherical harmonics have to do with the state of the orientation of the angular momentum for the M and the total angular momentum for the L, which we hadn't talked about angular momentum, so I had to come there. Obviously, you need Rodriguez formula to calculate that polynomial for each case. And you know what I don't want to do at all? I don't want to at all use this formula in the box. I want to rely on anyone could put the equation together. So, I mean, I could have you calculate one for homework, but I'm not going to have you do it a bunch because it's really not that useful to you. So this is how we identify the spherical harmonics. Y0, 0, that means L is 0, M is 0. Y11, Y10, that means L is 1, M is 0. And then we have Y1 minus 1, Y2 minus 2, and so on. What are some rules you can tell me about these? Remember, these are solutions to the Schrodinger equation, so they're part of the wave function. And what do we learn about the wave function rules it has to obey?
M can be, well, the M squared, so it's plus or minus.
Basic quantum physics stuff, not specific to this yet. Just basic quantum physics. It's about the wave functions. They have to be. We have two things we say all the time.
No. Well, they have to be normalizable.
And
they, I want to say they have to approach 0, if I remember right.
That is, if you approach an infinite boundary, by infinite, if a boundary infinitely far away, the wave function has to approach 0. That's what you're saying. And that's to be normalizable, that has to be the case. But then there is also, each one has to be orthogonal. They all have to be mutually orthogonal.
Yeah.
So let's just check and see if these are orthogonal, if they're normalized. So let's start with the first one, Y00. That's just a constant. Well, how do I check to see if that's normalized?
Well, your Y star times Y of the whole space, so negative, negative.
Not so.
Equals 1. Sorry.
Not going from negative infinity to infinity here. What are the variables of Y? Yes, you do. What are the variables of Y? I thought I heard you say, I don't know.
No, I was saying, well, we have M and L as our quantum numbers.
Okay, M and L are the quantum numbers. But the variables, Y is a function of what?
Is it theta phi or phi theta?
Yeah. Y is a function of theta and phi. So that means my integral is going to be an integral over theta and phi. But not so fast. We don't just put d theta, d phi, right? What do we have?
Well, we have a double integral. We have an integral and an integral.
The entire wave function, psi, a function of r, theta, and phi, is going to have dv is equal to r squared sine theta dr d theta. Excuse me. So in this case, we're going to have our d is this r squared isn't going to be part of it because we're not having the r function. I think that we still put in the sine theta d theta d phi. Now, I did not do this beforehand because I was going to just lecture, and it wasn't until I sat down I was like, let's play with these. So let's hope that I did that right. Actually, let's look in the book. I'm betting the book did this. Go ahead.
And well, if that's true, do we just normally drop R squared D on?
I did that because I'm not dealing in the radius space. And so my integral is not going to have an integral over radius in it. So I just dropped out the parts that have R. But that's kind of a gut reaction rather than any mathematical surety. Okay, so I don't see the textbook actually doing this calculation. So let's see what we get. Go ahead.
They say in the textbook they have on page 138 they have well your integral 0 to 2 pi, integral 0 to pi, y mod squared sine theta. So
yeah, okay, yeah, they do have what I have. Right, they have the R stuff in front, and then they have this integral. So let's do this. So if it's a constant, that's kind of easy, right? Oh, and the limits. It's in,
they're flipped in physics, right?
yes.
All right, so 0 to 2 pi for phi.
Yes.
0 to pi for theta.
So there we have it. I use colors to code them out there. And this one here is going to be easy for us to do because psi is a constant, so I can actually bring that constant out front. Integral from 0 to pi of sine theta d theta, integral from 0 to 2 pi of d phi. Now, you being a mathematician, I am pretty confident that you can do these integrals. So what's the first one?
So we have the integral of sine is negative cosine. And that's from 0 to pi. And then we have multiplied by just 2 pi. Or 2 pi minus 0.
Or 2 pi minus 0, yeah. Okay, and then we do cosine. What's cosine of pi?
Cosine of pi is going to be 1. Well, this is negative cosine. And then you have minus a negative or plus.
Cosine of 0 is 1.
Yeah.
So that's 2 times 2 pi. Well, that's 2, right? So 1 over 4 pi times 2 pi is?
Wait, what?
Okay, this
That's 1.
yeah. So sure enough, that's normalized. Good enough? Okay, so now that's only the y00. That was pretty lame. Let's do the y11. And after you do the y11, then we'll check to see if y11 is orthogonal to y10.
Okay.
So we're doing this. Now I have to, of course, look. And it's root 3 over 2 root pi. Since we have two of them, that's going to just be 3 over 4 pi. Do that right? Oh, and sine cubed and squared.
Where did you get the sign?
Okay, let's write the intermediate. So there I've put the fixed parts. And then I have my y star, which is
Yeah.
and then I have my y, which is, come on, the same thing. And so just counting up, 1, 2. Oh, I'm sorry.
Oh. Never mind. I was looking at Y11 to the.
You're looking at this one here?
Yeah.
Sorry. I thought you were saying, how did I get the powers of 3 and 2? I thought you were saying where I got the powers of 3 and 2 here.
No, I was wondering where the extra.
Yeah. Okay, so now we have to do integrals of sine cubed and sine squared. Sine squared is kind of easy because sine squared is just going to be an average of 1/2. 1/2 times 2 pi is the answer there. Sine cubed is a little more difficult. I would look that up in an integral table if I were you. And I don't think our textbook has that in it, does it? No. Oh, great. YouTube.
They probably break it apart.
Yeah, which is not what I really care about. I don't need to have it prove to me what it is. Although apparently everybody wants to prove it. Okay. Integral of sine cubed is minus cosine plus cosine cubed over 3.
Oh, yeah. You split it apart.
Remember I said the average of sine squared phi is just 1/2. 1/2 times 2 pi gives me pi. So that's why I did the second one in my head.
Yeah.
So we've already done the minus cosine. We know that gives us 2, right? And then cosine cubed is going to be cosine squared is just going to be 1 in both cases. So it's really going to be the same thing, except for we had over 3, and instead of a minus, or instead of having a minus sign here, we have a plus sign, so that means that it's going to be negative. Two minus 2/3 is 6 minus 2 4/3. Bueno. Now, I know you're a math major. You might be doing these things faster than me. But do you understand my argument for this one?
Yeah.
Okay. I was identifying that at pi, cosine squared is 1, and at 0, cosine squared is 1. Hence, I used the same idea as we used for the first one. So there we found that that's normalized. 2 is enough to prove it for me. Now let's check the orthogonality. Okay, so then we're going to have our constants are, I can't remember what the first one was, 1 over 2 root pi. I forgot one thing, of course. Forgot to put my d phi right there. Okay, so let's do this bad boy. All right, let's just look at the two integrals. What do we get for sine squared theta integrated from 0 to pi? It's pi over 2 because the average of sine squared theta over a half cycle is still 1/2. And 0 to pi, you just multiply then by pi. Excuse me?
No.
Okay, so that's not 0. This one here has to be 0, or else it's not normal or orthogonal. Integral, what's the integral of sine phi? And because we had to have our periodic boundary condition, we had to choose our integers for this argument of phi, so that cosine of 2 pi is equal to cosine of 0. So this one here is the one that gives us 0. So those two were orthogonal, and I'm not going to do any more of those tests. I believe in your homework you will have a few of those tests. Well, here you've seen exactly how to do it. Oh yeah, I was like, where'd everything go? These pictures here are pictures of what the actual orbitals look like. We will go look at these pictures after we finish the radial solution, because you don't get the orbitals without having a radial solution. So let's go to, wow, yeah, I used up most of the class period on that. Let's go to something that's a little bit newish. Not the Saint Schrodinger. So now we're going to look at the radial solution. Something that's specific. So our potential energy function here is a function of R. What is it for the hydrogen atom? I have it written in a slide below, but we usually write it like this. We usually write it like that. Well, in this case, the charge in the nucleus is plus E. The charge of the electron is minus E. The total potential energy is negative, so we'd have minus KE squared over R. So that's our potential energy function. We're going to define a new variable. You notice these solutions are much harder than the ones we did up to this chapter because reality doesn't have all the nice smooth corners that textbook problems do. And so the methods show you the originality that mathematicians really have to solve these kinds of things. My gut reaction is never to invent a new variable that's R times my function, or a new function that's R times my function. It just does not seem like a reasonable way. And yet that's what we do. So I want to go ahead and show the relationship between those terms. Now, it's important to do another notice another thing before we get started. This here had 1 over R. And it had the energy over here. We're going to move the energy across, move the L times L plus 1 over there, and we're going to multiply by R, and we're going to multiply everything by lowercase r. So everything is going to be multiplied by R, and we're doing those switches. So if we do that, we would have, I shrink this down so I can not forget. Oh, one more thing. One more thing, we are multiplying by minus h bar squared over 2m again. Over 2mr squared. I forgot about that step as well. So all of this is being multiplied by that whole crazy thing. Notice that I can actually cancel one of these r's. Whoops, I just wrote canceling 2. Yeah. We'll see if I have the right thing multiplied. I think that's what we're doing, but we'll see in the end. There's my first term. I want to get my sign straight. Okay, so I combined the term that I brought over, so that's why it has a minus sign here. And yeah, I believe I preserved all signs. Sorry, I'm going very slow. Okay, so that should be the conversion back, which seems pretty long and hairy. But now we cancel that. So there's our first term. I'm going to check here to see if I want to put a minus out front or not. To make it look the same, I'm going to put a plus out front, okay? Yeah, I could cancel with this term, but not with the next one. And mathematically, you can't write it as if you're canceling when you're only canceling with some of them. It served its purpose. So I pulled out an R, so that's going to be over R squared because I pulled out an R. Now, I fear I have a sign wrong. Nope, I don't. Huh. Will the miracles ever end? Minus and minus is a plus. Here I can actually cancel. So that is our new equation. Now notice we define this is u, that's fine. This is u, that's fine. Over here, we'd better check. So according to what we have, this here should equal that there. Now let's not worry about the h bar squared over 2m, but do notice that this has no r and this has the over r. Whoops. And this has the over r. So what we want to do is to show that this here is equal to that there. So do that one first. Just a single derivative, so we just have the product rule. That one's kind of easy. First derivative. Second derivative. Now, I didn't expand this last one or the top one out. That's a 2. And we see, voila. I saw something again yesterday on Facebook where somebody put, and voila. Actually, they put WOLLA. That ain't it. Voila. I don't know how people get through school sometimes. Or maybe they didn't. So what we've done with all of this work that took basically the rest of our class period was justifying that this equation here is equivalent to this equation here. And then we're going to define an effective potential that's the potential plus this term here that's called the centrifugal term, because it has the effect of a force that's pushing away from the center. So we've done very little that will be disruptive for Indy missing it, but stuff that should help you in understanding better. Any questions?
So other than what exactly is the point of, I know this will probably go into the next period, but what's the point of having the effective potential? Having that, we have our potential B, but then we also have the additional. Why is that? Is that something that? Because I know we talked about this back in university physics, how it was something that's a pseudo force.
Well, centrifugal force is a pseudo force, yes, or fictitious. Well, this term here, it appears because of the going back to when we split the equation. Remember how we split this out? We had this thing on the left-hand side had to equal a constant. And so because of the position of r squared right here, when we reconvert things essentially back to where they were before we started, that r squared moved to under here, giving it a 1 over r squared term with a positive sign. The negative sign is centripetal toward the center. Positive sign is centrifugal away from the center. It's not representing a real force. It's representing a force necessary actually to hold it in. If it's spinning, you're going to need additional force holding it in for the radius compared to what it would be if it was stationary there. And that's what it really is representing, the additional you need to hold it in place because it's spinning. Okay, so we'll pick up. You're saying? We're good at talking to each other.
I'll see you Monday.
Yeah, I do have an announcement for you and Indy. I got an email yesterday indicating that next Friday you guys have a modified schedule. And the time for this class is in the middle of my physics class. So I can't be here during your class period next Friday. At this point, I've kind of given up on us having additional class periods, except for we will have our Tuesday office hours. I think we'll just have to consider that gobbling up the additional class periods.
I mean, if it's okay with me, that'd be fine. If we can cover material during that Tuesday period. But I'll have to talk to you.
Yeah, well, I do want to actually give you a chance to go over homework questions, especially the timing of it being Tuesday and homework doing Wednesday. It's kind of prime time we chose for that purpose. But we won't have class next Friday no matter what. Okay. Unless, I mean, you guys are doing your community service in the afternoon, is that right?
This coming Friday?
Yeah.
You know, I'm not sure. I haven't really checked. Who sent you the email?
The person who's the coordinator for the AEA classes. I can't remember her name.
And they said we had community service or something?
Yeah, it's Community Services Day.
Okay. I'll have to check our schedule because I guess I wasn't aware that.
Okay, well,
Yeah, I'll have to check it out.
actually, yeah, I'll check the email and tell you exactly what it says, just so you. I mean, you guys will probably talk about it more coming up. Yeah, at your school.
Yeah. I was gonna say, it's interesting that you mentioned that because my brother's actually coming down next Friday. I did not realize that we had something going on.
Okay, Tammy Overstreet is the person who sent it, and she said, "Oh, it's Southwestern." Well, Southwestern, that's not a problem.
Okay.
So we're good. We're good. Okay, class is normal next week.
Sound good?
All right.
See you.
See ya.